So we've said time and time again that the most important thing in solving a work energy theorem problem is to identify the type of energy that is being changed. Okay? So in number one, what kind of energy is being changed in number one? Kinetic, it's speeding up. Number two, potential, the height is changing here. Okay, so that's our first step for both of them. All right, so for question number one, give them a mark for their givens. We know the mass is 200 kilograms. The initial speed is 2 meters per second. The final speed is 8 meters per second. Okay, the distance there is 13 meters. I've got to correct my significant figures here in just a sec, so don't panic on that one. Okay, another mark for identifying it as a work energy theorem problem. Okay, where the kinetic energy is being changed. Okay, so if they got something like either one of those, they can have that mark. We are manipulating here for the force used to do the job. Yes. They should have K. They should have K there, yeah. Yeah, it should look like that actually. Okay, and then our manipulation to get force by itself is to divide both sides by distance and bring it over here. So another mark if they've got it manipulated correctly. Another mark for plugging in their numbers correctly. 1/2 times 200 kilograms times 8 squared, the final speed, minus 1/2 times 200 kilograms times 2 squared, divided by 13 meters. And that should give us to two significant figures. 4.6 times 10 to the 2 newtons. Questions on number one. Okay, how do we know it was two significant figures? I go back here to my original question. Okay, two significant figures, two significant figures, three significant figures, two significant figures. The rule is you go with the lowest number, 2. All right. For our second question, okay, give them a mark for their givens. The mass is 65 kilograms. It's raised from a height of 13 meters to some unknown height. Okay, and the work done in doing that is 450 joules. All right. So if I've already got the work in here, am I going to be dealing with force and distance? No, because I already know what they multiply together to produce. Okay. So next mark. Okay, we should have work as a change in potential energy, or maybe they went work equals mghf minus mghi, either one. Okay, that's their second mark. Their third mark, okay, if I want to get my final height, okay, right here, what I need to do then is add mghi over to the other side. Okay, and then I'm going to divide both sides by mg in order to get hf isolated. So I'm going to add mgh, which I've done here. Okay, divide both sides by mg. Nothing's canceling here because I've got an operation on the top already. Okay, so give them a mark if they got to this point here. Then we've got to plug in our numbers, so that's another mark, 450 joules plus 65 times 9.81 times 13. So really what I'm doing here is I'm saying take my initial potential energy, add the change in potential energy, okay, divide by mg, and I've got my final height. Okay, everybody all right with that? All right, so a mark there, and then a mark 4, and this should only have two significant figures, so it should be 14 meters, okay, as their final height. So 5 marks each. Please give them a total out of 10 at the top. Let them see it, and then we'll collect them on the desk in front of Evan over here. So, had a number of people asking, how come M and G don't cancel here? Okay, the answer is, first off, because there's an operation on the top that has to be completed first. Okay, if I cancel off M and G, then I'm no longer saying that work is a change in energy. I'm saying that work plus height equals energy. Is that true? It isn't true. Or that work plus height equals height. So joules plus meters equals meters? That's not true. It's not mathematically true for me to calculate those, to cancel off those two things. All right, everybody follow me there? Okay, so when in doubt, don't cancel, right? Or if you've got an operation on the top, especially addition and subtraction, don't cancel something off if you're dividing. Okay, it just doesn't work that way. Okay. All right. We ended off class looking at this this application question here. We had an average force of 40 newtons is compressing a spring 0.1 meters. What can I calculate if I know force and distance? work. All right, so I'm going to calculate the work done in compressing the spring by going 40 times 0.1, which gives me 4 joules. Okay, fairly straightforward calculation. What happens to the work done on the spring? So if I push in on the spring, what does the spring now have? Potential energy. Okay, that's what happens to the work done on the spring. It is now stored as elastic potential energy in the spring. If the spring is released, what happens to the energy of the spring? Yeah, it'll turn into kinetic, or if something is placed in front of the spring, it'll transfer energy, which is called work. Okay, it'll do work on something else. All right, calculate the energy that the ball has the instant it leaves the spring. Well, if I do 4 joules worth of work, how much energy can the ball have? 4 joules, that's all. That's work energy theorem and conservation of energy together. What will the speed of the ball be if it leaves the spring? All right, here's the mass of the ball. Okay, 1.0 times 10 to the minus 2 kilograms. In other words, 0.01 kilograms. Okay, and we know it has 4 joules worth of kinetic energy. So 1/2 mv squared equals 4 joules. Can we calculate how fast it'll be moving? Okay, so we go m equals 4 joules divided by 1/2 times 0.01. Okay, and when we do that, sorry, not m, v. Sorry. Okay, so the square root of all that will give me v. Okay, and it comes out to 28.3 meters per second. Okay. Everybody all right with that one? Okay. If the ball is fired straight up in the air, how much energy is it going to have when it's at its highest point? 4 joules. Still, that's all the work we did on this system. That's all it can ever have. Okay. What's the maximum height it can rise to? Same idea here. We're going to say that 4 joules equals m times g times h, and solve for h. So we'd have our 0.01 times 9.81. Okay. Leaving us with h, and that h is going to come out to 40.8 meters. All right, we've done all that kind of stuff already, just kind of a quick review of that. Okay, I want you guys to do 7 and 10. 7 and 10, please. Okay, working on 7 and 10 right now. Okay, and then we're going to go into something else here. All right. So on number 7, we have this billiard ball that's propelled at a speed of 1.5 meters per second. So does it have kinetic energy? Yes. It's also above the ground, so it has potential. All right, how do we calculate mechanical energy again? It's potential plus kinetic, right? Okay, the potential energy plus the kinetic energy, so that'll be m times g times h plus 1/2 mv squared. Right? We have all of those numbers. It's 0.3 kilograms times 9.81 times 1.3 meters. Okay, that was our height. And we've got 1/2 times 0.3 times 1.5 squared. Right? And when we do that, we should get 4.16 joules. We'll just double check though. Right, so 0.3 times 9.81 times 1.3 plus 0.5 times 0.3 times 1.5 squared. 4.16. Okay. Everybody all right with that one? So that's just a calculating mechanical energy kind of question, not even a law of conservation of energy question. What's the matter? Okay, I just put it in from left to right. I didn't even put any brackets in. And my calculator did order of operations for me. I remember into square feet. Okay. And you're using 1.3. You're not confusing the 1.3 and the 1.5 here? I'll have to come and have a look in a sec, Carly. Okay. Here's one that we're going to try together. This is where, by the end of this unit, we should be in terms of questions we can answer about the law of conservation of energy. So I'm going to have you guys try this. So first I'm going to explain it, then I'm going to have you guys try and solve it. We did one like this yesterday. Okay, I have a 1,600 kilogram roller coaster at the top of a 50-meter hill. It is moving at 5 meters per second. A little while later, it is near the bottom, 8 meters above the bottom. I want to know how fast it's going at that point. Okay, the thing we have to remember here is that the mechanical energy here at the top of the 50-meter hill is the same as the mechanical energy down here. What's different is how much of it is potential and how much of it is kinetic. All right, I'm going to give you guys a few minutes to try that one. Starts out like this. Remember, we said the mechanical energy at this position is the same as the mechanical energy at this position. Okay, so this is initial mechanical and final mechanical. How do we get mechanical energy again? Okay, so my initial potential plus my initial kinetic equals my final potential plus my final kinetic. Okay, I'll give you a few more. All right, so we're looking for the final speed of the roller coaster. That's going to be part of which one of these terms? EKF. Okay, because it's kinetic energy. It has to do with kinetic energy. We're looking for that. It's VF, but it's part of this one. Okay, so I want to get this one by itself. What should I do with EPF right now then? Subtract it, right? I'm adding it right now. I subtract it over to this side. So really what I'm saying is the mechanical energy minus the potential energy equals the kinetic energy, right? Fine. In this case, the final kinetic, right? That's all I'm saying when I do this. So I'm going to have EP initial plus EK initial minus EP final equals EK final. All right, now I'm going to plug in my formulas. Okay, so I'm going to have M times G times H initial plus 1/2 MVI squared minus MGHF equals 1/2 MVF squared. Okay, all I've done is put in the formulas for kinetic and potential energy. Okay, that's all I've done. Okay, now that I have that, this is what I'm looking for, VF. How do I get VF by itself? Divide both sides by 1/2 of M. Okay. And then I'll square root, yeah. All right, so guys, even though I've expanded it out and it looks a lot busier, it's still saying the same thing it said before, okay? Potential plus kinetic is mechanical, minus potential gives me kinetic, okay? Now I'm just isolating my speed, okay? All right, if at this point I wanted to, could I cancel off all the M's? I actually could at this point cancel all the M's because M is part of every term, okay? Because it's part of every term, I can get rid of it. Okay, if you're not comfortable with that, leave it in. It won't make any difference mathematically to the answer. It's just more stuff to punch into your calculator. Okay, all right, so when I punch all of my numbers in, okay, I'm going to have the square root of, what was it, 1,500 or no, 1,600. Okay, 1,600 kilograms, okay, times 9.81 times 50. So there's my initial potential energy, plus 1/2 times 1,600 times the initial speed, which was 5 squared, minus, okay, 1,600 times 9.81 times 8, my final potential energy. Dividing all of that by 1/2 of 1,600 and square rooting it all, that'll give me my final speed. Okay, now when you're punching this into your calculator, it's a bit of typing, right? What I do is I just kind of do it one piece at a time. So I'm going to have my 1,600 times 9.81 times 50. All right, so I've got that number. Now I'm going to add that to 0.5 times 1,600, so I'm doing my kinetic energy now, times 5 squared. Okay, so now I've got the total mechanical energy at this point. Okay, I have the total mechanical energy. Now, I'm going to subtract my m times g times hf. All right, so that's going to be 1600 times 9.81 times 8. Okay, now I'm going to divide by half of 1600, which is 800. Okay, and then I square root. Whoops. Not what I want. Not squared. Okay. So on the top of that hill, it's going to be moving at 29 meters per second. All right, yeah, it's a lot of typing. But guys, honestly, it's all the algebra stuff we've been working on. This is the most manipulation. This is the most manipulation that you will have to do. Okay? In any equation or problem that we do in this course, that's the most manipulating you're going to have to do. But it's not any different than what we did before. Okay? We're still following those same 2.5 rules. If I want to move something, I do the opposite. What I do to one side, I do to the other. And I move what's not attached to what I'm looking for first. I did all of that up here. What I was looking for was part of EK. So I moved this. It wasn't attached to it. I got rid of it. Okay? Then I had to move 1/2 of m. I did the opposite by dividing because I was multiplying. And then I did it to both sides. Okay? Then I square rooted both sides. All I did was follow those same 2.5 rules we've been following the whole unit. Okay? It's going to take a little bit of practice. We've got lots of time for that. Okay? Questions on that one? Okay? It's very similar to what we just did. It's just not a roller coaster, it's a toboggan. Okay? So here's our hill. There's the toboggan. Okay? The top of the hill is 30 meters higher than the bottom, and it's moving at 14 meters per second. So I guess not quite the top of the hill, but it's somewhere higher than the bottom of the hill. Okay? How far above the bottom is it when it's moving at 23 meters per second? So we're looking for H final. This is our situation. We know that early on it's 30 meters higher, 30 meters above the ground, moving at 14 meters per second. A little while later, it's moving at 23 meters per second. The only way for that to happen is for it to be lower down the hill. We're looking for how high above the bottom of the hill is it at that point. Okay? I'll give you a few minutes to try that one. All right. We know that in a question like this, the initial mechanical energy and the final mechanical energy are equal. Okay? No one's pushing the sled. Okay? It's not losing any energy at any point. Okay? So the energy at the beginning is equal to the energy at the end. Okay? At the beginning, oh crud. At the beginning, okay, it has potential energy because it's 30 meters above the ground. Okay? And it's moving, so it has kinetic energy. So I'm going to put that in here. Okay? Initial potential plus initial kinetic. That's my initial mechanical energy, which is the same as my final mechanical energy. And at the end, I'm moving, and I'm still above the ground. So I also have both kinds at the end. Everybody with me so far? What I'm looking for is part of which one of these? EPF. All right, so I want to get that by itself right now. What do I do with EKF? Subtract it over to the other side. So my initial potential plus my initial kinetic minus my final kinetic equals the final potential energy. Okay, everybody with me so far? Really all I'm saying at this point is mechanical energy minus kinetic equals potential energy. Okay, that's really all I'm saying at this point. Now, I can plug in my formulas for all of these. Okay, at this point I have to do that because now I'm looking for an individual variable. right? So for initial potential, that's m times g times h initial. For initial kinetic, it's 1/2 mvi squared. For final kinetic, minus 1/2 mvf squared. That's going to equal m times g times hf, my final potential energy. So all I've done is go to my formula sheet and plug in the formulas for EP and EK. Now, mass is in every single one of these terms. Therefore, I'm multiplying everything in this by the same number. Does that number matter? It does not. No, gravity does not cancel out because it isn't in every term. Right? You can't cancel gravity. It isn't part of kinetic energy. Okay? So it doesn't go away. It can't. Okay? Now, I've got to move G over to this side. I've canceled off M, and I'm looking for H. So I just divide both sides by G. Now H is by itself. All I have to do is plug in my numbers.
So the G cancels out.
No, I just said the G does not cancel out. G is not in every term. It doesn't matter. I didn't divide all. I have to divide this whole top part. There's addition and subtraction. If there's addition and subtraction on the top, I can't cancel something by dividing on the bottom. It doesn't go away. If it was just this, m times g times h over mg, yes, then they would both cancel. Oh, yes. Yeah, when I moved it over here, yes. Yeah. Sorry, I thought you meant it canceled from both sides. No, it doesn't. Okay? Yes, it cancels because I moved it. Yeah. No, I don't square root that because h isn't squared. Right? H is not squared here, so I don't square root. I'm just solving for h. Okay? So now I'm going to plug in my numbers. 9.81 times 30, so that's my initial height and gravity, plus 1/2 times 14 squared, there's my initial kinetic, minus 1/2 times 23 squared, my final kinetic, divided by 9.81. That's going to give me my final height. All right, so 9.81 times 30 plus 0.5 times 14 squared. Minus. Okay, guys, got to watch carefully here, okay? These are huge marks on your test. If you're not paying attention, laughing isn't going to make you better at it. Okay, simple as that. Yep.
Yes.
13 meters. See, there you go. So it's 13 meters above the ground here, not 30. Okay, 13 meters. Now, just to prove that mass cancels, and it's okay. If you didn't cancel mass and you put something in for mass, okay, it's no big deal. I'm just going to pick a number and put it in for mass and do the same operation. I'm going to get exactly the same number. Right? So I'm going to say the mass was 30 kilograms. Okay, so that's the height and that's the mass. Okay, plus 0.5 times 30 times 14 squared. Okay, minus 0.5 times 30 times 23 squared. All right, and then I'm going to divide that by m times g. So divide that by 30 times 9.81. Mass doesn't matter. I could put in any number I wanted, and it'll still come out to the same number. Nope. It just take you longer because you got to enter it in 4 times.
But you could only cancel out mass if everything has mass.
Right.
If
If every term that you're using has mass in it. So up here, every term I was using was multiplied by m. Right. There isn't going to be a situation like that I can think of, but yeah. All right. Try that one. Okay, let's just look at the start of this one. We won't go all the way through it, but okay, let's just look at the start of this one. Okay, if you drive off of a cliff, that's not a good idea, first off. Okay, but if you drive off of a cliff, what kind or kinds of energy do you have? Kinetic and potential. You've got speed as well as height. Okay, so we know that initially we've got both kinds of energy that are part of mechanical. At the end, however, you're striking the ground. So you don't have any what? You don't have any potential because your height at ground level is 0. All right, so what we're starting off with here is that EP initial plus EK initial, I have both, equals EP final plus EK final, except that because the height is 0, I don't have any of that. Okay, which simplifies my work a little bit. It's one less thing I have to worry about. Now, what I'm looking for is how high the cliff is. In other words, I'm looking for initial height, which is part of this term. So I want to get this term by itself. What do I do with this? Subtract it over to this side. So I'm going to have EPI equals EKF minus EKI. All right, now I can plug in my formulas because that's as far as I can go with just the terms. Okay, now I need the individual variables. So M times G times H initial equals 1/2 MVF squared, so that's my final kinetic, minus my initial kinetic, MVI squared. All right, what's in every term? M. Since they didn't tell me what the mass of the car is, that's a good indication it wasn't something I needed anyway. No, you wouldn't lose marks for that, but it's going to come out to 0. I always eliminate it early so it doesn't confuse me. I don't go looking for things I don't have, right? Okay, I want HI by itself, so what do I have to do with G? Divide both sides by G. Okay, so when I plug in my numbers, that's going to be 1/2 times 53 squared minus 1/2 times 25 squared divided by 9.81. Okay, so the cliff was 111 meters. Actually, I think this only has 2 significant figures, so 1.1 times 10 to the 2 meters would actually be our correct answer here. Okay, that one was on last semester's unit exam. Okay, that question was last semester's unit exam question on law of conservation of energy. Okay, so I didn't even make it one that had both kinds of energy at both points. Okay. Questions on that one? Okay, try this one. Similar to what we just did, okay? They're all the same, really. They're all the same. You're either going to be solving for a speed or for a height. All you have to do is isolate it and plug in the numbers. Okay? They all work the same.